Hello friends. So today I'm going to discuss, as I mentioned on my last lecture, that simple and compound proposition, and on the last lecture I discussed some of the implications like converse, inverse, contrapositive, and I also had discussed biconditional proposition. So hope you guys have understood those topics well. So today I am starting with simple proposition. So as from the name, you can assume that simple proposition where the proposition is simple, like where only one proposition is involved, that is called simple proposition. So then what is compound proposition? When more than one proposition is involved, that is called compound proposition. So let me take you to an example. Like there is a function consists of p and q variable. So negation p conjunction q. So here is the truth table for the function consists of p and q variable is so pq is as follows, and negation p is f true. So negation p conjunction q is f t f. So it just follows the basic rule of conjunction, and then negation of this one. So it's false, true, false, true, true, false, and false, true. So this is called a compound proposition because here more than one propositions are involved. So now there is a formula that the truth table of a propositional formula consists of n variables will exactly have 2 to the power n number of rows. So if f function of pq is a formula of two variables p and q, so the truth table of function of pq has 2 to the power 2 is equal to 4 rows. And now is tautology. A proposition or statement formula is called tautology if it assumes only the truth value t. Like in very simple form, the last column of that propositional formula will be all true. So let me take you to the example. Like this is a function consists of p and q variable, and this is the propositional formula of this function. So this is the truth table of this formula. So we can see that the last column of the proposition formula is all true. So this is called tautology. So contradiction is just the opposite of tautology. So the last column of the truth table will be all F. So let me take you to the example. Like this is the propositional formula, consists of variable p and q. So this is the truth table. So we can see the last column of this propositional formula is all F. So this is called contradiction. And now logical equivalence. So two proposition will have logical equivalence when both their truth tables will be identical, or the last column of that truth table will be same. So then we can say that those two truth tables has logical equivalence. Like consider P implication Q and negation of P disjunction Q. So here are the truth tables of those two proposition. So we can see that the last column is same for both the truth tables. So we can say that both the truth tables or both the propositions have logical equivalence. So therefore P implies Q is have logical equivalence with negation of P disjunction Q. So now algebraic laws of connectives. So why we need these laws? The answer is whenever we need to simplify any propositional formula, then we will need these formulas or these laws. So let PQR any proposition, then P disjunction to P will have logical equivalence with P, and P conjunction P will have logical equivalence with P, and this is called idempotent law. And the next law is associative law. So P disjunction Q disjunction R will have logical equivalence with P disjunction Q disjunction R, and P conjunction Q conjunction R will have logical equivalence with P conjunction Q conjunction R. This is called associative law. So these two are the algebraic laws of connectives.